Hello, this is Ms. DB, and today we are going to continue in Chapter 7 with Section 6 on the natural base e. Our objectives are to use the number e to write and graph exponential functions representing real-world situations, and of course to solve equations and problems involving e or natural logarithms. So e is a number. It says that here, and that is correct. It's a special number that we use when we're dealing with logarithms. Remember, the compound interest formula is a equals p times 1 plus r over n to the nt power. A is the amount, p is the principal, how much you put in at the beginning, r is the annual interest written as a decimal, n is the number of times the interest is compounded per year, and finally t is the time in years. So if we had $1 invested at 100% interest, which would be r equals 1, compounded n times for 1 year, is represented by the function, it would be f of n equals p times 1 plus 1 over n to the n, because 1 year is t. So this is what it would kind of look like here. We would have, as n gets very large, interest is continuously compounded. So as n gets bigger, like if n was 1, it would be 1 time a year, which would be silly. If n was 12, it would be 12 times a year, once a month. If n was 365, it would be each day. And you can see that when it's only compounded 1 time, it's right here, and then it gets more and more money. But it doesn't go straight up. It's not like if it's compounded continuously, you make tons more money. It's going to approach this line right here. See that line? And that line is our number e. And e is the number 2.7182818, and then there's a few more digits after that. That's where e comes from. It's like pi. It's a constant. It's an irrational number. It is a number that we can use like a number, even though it's a letter. We can work with it just like we can with pi. Exponential functions with e as a base have the same properties as the functions you've already studied. So the graph of f of x equals e to the x is like any other graph of exponential function, like 3 to the x, or 2 to the x, or 21 to the x. It's just a number. E is a number, a special number. The domain of f of x equals e to the x, it's also the same as it would be for any other exponential function. All real numbers will be the domain, and the range is going to be the positive numbers, so y greater than 0. It won't have negative values. The decimal value of e looks like it repeats, but it actually keeps going on. There's more digits after that. There's no repeating part. It's like pi. It's irrational. The digits will continue. There hasn't been found to be an end to it. All right, let's look at graphing exponential functions where you have e as a base. And again, this is not going to be any different than if the base was some number other than e. So one method is to make a table. We will have to round because e is irrational, and you'll have to use a calculator to find these values. Here's the values that were calculated for the different values of x. And then you would plot your points and connect them, and you'd get that smooth looking curve. You can also, of course, use graphing technology. In Sketchpad, you'll want to, if I have this problem set up, if you want to graph an exponent that has more than one number in it, like this is 3x for the exponent, then put parentheses around the 3 and the x. Also, to find e, you go to the values menu, and there it is there. Pi is there as well. And then we use to the exponent. Now watch what happens if I just put 3x. It went e to the third times x, and when you graph this, it's going to look linear. Because e to the third power is just a number, and then we're multiplying by x. This is a linear function. That's not correct. Instead, I need to go back and put parentheses around the 3 and the x so that I know that it is both parts of that as part of the exponent. Now we've got our logarithmic function there. So that's pretty basic. At Desmos, the only thing to remember in Desmos is you can't find E in a value table like in Sketchpad, so you just type the E on your keyboard. So I'm not even going to show that one. All right, so a logarithm with a base of E is called a natural log, or a natural logarithm. It's abbreviated ln. Now it maybe should be NL, but we use ln for natural log. So we don't write log base E, we write ln. Remember that the common logs are just written log, L-O-G. That's really base 10. So if you see ln, that's really base E. So this is base 10, this is base E, but we don't write the bases around those two special ones. So they have the same properties as other logs that we've worked with. It's just that they're special logs with a special base. So it's called the natural log, and it is the inverse of the exponential function e to the x. And if you graph both of them, they will be symmetric about the line y equals x, and they are inverses of each other. Just like we learned in a previous section, the inverse of an exponential is a log, and the inverse of a log is an exponential function. The domain of our f of x equals natural log of x is positive numbers, or x is greater than 0. The range of natural log of x is all real numbers. It can be negative, it can be positive, which, as you can see, would be flip-flopped from the domain of e to the x would be all real numbers, and the range would be y greater than 0. All the properties that we learned from lesson 7.4 also apply to natural logs. Here's an example of simplifying. We're going to do a lot of these on the worksheet. And here's the key. We're going to use the same properties as before. So in this one, the exponent can be written in front. And here's the key part. When you see natural log of e, that's equal to 1. Because natural log of e, that's really the same as log base e of e, and that's just equal to 1. Because if we wrote this in exponential form, we would have e to the what is equal to e. So of course it must be 1. So the natural log of e is equal to 1. So this right here is equal to 1. So we'd have x plus 2 times 1. That's just x plus 2. That's as simple as you can get. So you're not always going to get numeric answers. You might have an x in your answer, but it'll be simpler than what it originally was. All right, let's look at the next one. If we had to simplify e to the power of 4 natural log of x, then again we can put the, this is the power property. We can take the 4 and use it as an exponent on the x. So this is e to the exponent to the power natural log of x to the 4th. When you see e to the natural log of x, then that is equal to whatever your x is. So if you have e to the natural log of star, that's going to be equal to star. Whatever you're taking the natural log of, if that is your exponent, then it'll be equal to that exponent, that part of the exponent. All right, let's look at some examples. In the first one, we have the natural log of e to the 0.15t. Now remember that when we have the natural log of e, this part right here is just 1. So the answer is just 0.15t. In b, we have e to the 3 times the natural log of x plus 1. We can take the 3 and use it as an exponent right here. So put that over there. So that would be equal then to, I'm going to put the 3 there instead. And then when we have e to the power of the natural log, then this stuff is your answer. So x plus 1 to the third. You don't have to multiply that out. And in C, we have two things here. We're multiplying. Just like in logs, you can rewrite that as a power if you want to. But they said instead of doing that, just go ahead and say, here's the natural log of e, which would just be, this will be your solution there. So that's 2x. And then in the second part, we have natural log of e again, so then just the exponent. So 2x plus x is 3x. Okay, these are from your worksheet. This is 3, 4, and 5 from your worksheet. So in number 3, I would start by writing that as e to the natural log of x squared. And then when you see this, you can just use the rest of the exponent, x squared, and that's your solution. In 4, we have the natural log of e. So our answer is just going to be the exponent part of 1.8. And pretty much the same thing in 5, we have the natural log of e again. We're just going to use the exponent part of x plus 1. All right, now we'll get to some that are a little bit more complicated. When you have the formula for continuously compounded interest, we looked at approaching that at the beginning of this lesson. It is A equals P times E to the RT. A is the total amount, that's probably what we're looking for. P is the principal that you start with. R is the annual interest rate, and T is the time in years. And E, of course, is a number. It's a special number, and you can find it on your calculator. All right, here's the problem. What is the total amount for an investment of $500 invested at 5.25% for 40 years and compounded continuously? So first of all, you need to write the formula down. Then we need to say, well, what is A? That's what we're looking for. Okay, what is P? This is P right here. That's how much you're putting into your account. R is right here, but you have to change that to a decimal. And then this would be T right here. So T is going to be 40. And that's everything that we need. Now we plug those values in, and then you use your calculator. I'm going to show you how to use my calculator right here. All right, so on your calculator, you have to be very careful. The first thing that you want to do is figure out what is the 0.0525 times 40. 0.0525 times 40. You want to keep all of those decimal numbers. Oh, it's only 2.1. That's not bad. Now we need to take e to the 2.1. Now on my calculator, this is the standard computer calculator in scientific form. If I click this button, I get to other functions, inverse functions, and natural log functions. And now there will be an e. Where is my e? Here's my e. So I have e to the x. That's what I want. I want to take e to the 2.1. So I had to put the 2.1 in first, and then I click the e to the x, and that's what e to the x is. 8.166169999. Now I'm going to leave I'm not going to round to 8.2. I'm just going to leave it on my calculator and see what else I have to do. So that was e to the 0.0525 times 40. Now I have to multiply that answer by 500. So the whole thing is on the calculator, and I end up with 4,083.08. And at that point, you can round it. If I rounded before that, then my value would be considerably less, generally speaking, or maybe it'll be more. Watch what happens if I round too early, 0.0525 times 40. Now this was 2.1, which isn't bad. Let's say that I rounded that to 2, and then I took e to the x, and then I rounded that to 7.4. So now I took 7.4 times 500. So that's a ton of less money. So the rounding errors in this, by rounding each time, I got an answer that was considerably different from the actual answer when you put as much things into your calculator at a time as you can. Also, you can see if you're using a graphing calculator, you can enter all of the information at one time without having to make sure you're saving it, and you get that value as well. You can also use Sketchpad and Desmos as a calculator and enter as much information as you need to without having to hit enter until the very end. All right, here's a problem from your worksheet. Nemo deposited $1,000 into an account that paid 2.8% interest with continuous compounding. What was her balance after 6 years? So first you write down your formula. A equals P times E to the RT. We have our original amount is our principal, that's 1,000. Our interest rate, our R, is 0.028, and this is 6 years. So you plug all those values in. Then you use your calculator. Now they got 1,182.94. Just verify that with my calculator. So I need to take the 0.028 times 6 and then take e to that power. Then you multiply that amount by 1,000. Yes, I got the same thing. So you don't round till the very end. All right, then the last thing we need to discuss is half-life. The half-life of a substance, you may have heard of this in science class. It's the time it takes for half of the substance to break down or convert to another substance during the process of decay. Natural decay is modeled by this function. N of t is the amount remaining. N sub O is the initial amount. That's when t is equal to 0. Then we have our E. Then negative K is a decay constant, and T is the time. So you need to know the decay constant and the time. A lot of times you have to find out the decay constant before you can finish the problem. All right, plutonium-239 has a half-life of 24,110 years. How long does it take for a 1 gram sample of this to decay to 0.1 grams? So the first thing we have to find out is the decay constant, which you can do because if you know your original amount, let's just say it's 1, we know that this formula works if you put 1/2 over here. So we can put 1/2 here and 1 here. We don't know K, but we do know that 24,110 is the half-life, is the T that it would take for 1/2 to remain. So we need to solve this equation for K. So it's a good thing that you have learned how to undo exponential functions. You can take the log of both sides. Now, before we wrote log in front of both sides. When you're dealing with e as your base, you would write natural log ln in front of both sides. Very important. Whoops, I went too fast there. All right, so now the natural log of 1/2 equals the natural log of e. Now remember that earlier in this lesson we learned that that is an inverse, and we can just write negative 24,110k on the right side. On the left side, 2 to the negative 1 is the same as 1/2. All right, so now we're ready to rewrite. We can put our negative 1 here using our power rule in front. So that'd be negative log of 2, negative 1 if you prefer, equals negative 24,110k. And then you can divide both sides by negative 24,110 so that you can solve for k. So we're just dividing both sides by the number that is next to the k that's being multiplied. And now this is negative divided by negative is positive. So now you get your calculator out, and let me show you the natural log key on my computer calculator. And again, I had to push this button here. You might have to push a second function on your calculator or an inverse or some way to get to this part. And there it is right there, natural log. So I'm going to clear all this stuff out. I need the natural log of 2. And then I'm going to divide that by 24,110. So again, I don't round to until the end. Now it says e to the negative 5. That means, I can't use my calculator. I can't use my pen right now because I have this open. That means that that is to the negative 5 decimal places. So 1, 2, 3, 4, 5, and that's where the decimal would go. So this was really 0.0000287493. Not all calculators will show it that way, but do check at the back if it has something like that. Okay, now that we know what our decay constant is, it's 0.000029. Now we'll put that back into our equation along with our other information. We started with 1, and we want to know when would it be equal to 0.1. So we're looking for t here. So when we're trying to solve for t, again, that's part of the exponent. So we can take the natural log of both sides again, just like before. On the left side, we'll have to leave that as natural log of 0.1, or you can write that as natural log of 1/10, which is the same as the natural log of 10 to the negative 1. And on this side, we have just the 0.000029t. Oh, I thought they were going to rewrite that as natural log of 1, but they didn't. And then you use your calculator, and you find that it's about 80,000. So it takes approximately 80,000 years to decay. Okay, last problem. This is on your worksheet. It is how long will it take for 650 milligrams of a sample of chromium-51, which has a half-life of about 28 days, to decay to 200 milligrams. So there's two parts to this again. The first part is finding the decay constant. So we use 1 for our original amount, and we use half for what we're going to end up with. And we know it has a half-life of 28 days, so you put that in for t. So we're not using this information yet or this information yet. We first have to find the decay constant. So to simplify this, if you have to find a variable that's in the exponent, you need to take the log of both sides. In this case, we'll take the natural log since we're dealing with a base of e. So you take the natural log of both sides. On the right side, that can just be left as negative 28k. On the right side, that's the same as the natural log of 2 to the negative 1. Or you can write that as negative log of 2. Natural log of 2 equals negative 28k. So if we're solving for k, then at this point we need to divide both sides by negative 28. These will cancel, and you'll have positive natural log of 2 over 28, and then you type that into your calculator, and this is your decay constant. That's what we'll use now to finish the problem. We're half done. Oh, they didn't just ask for the decay constant, did they? So our decay constant is 0.0247. 0.0247. I must have cut something off of my slide. And now I have to use this formula in order to find the answer to the question. It says how long will we're going to look for t. How long will it take for 650 milligrams to decay to 200 milligrams? So I will put ignore this for now. I'm going to put n of t, that's the 200. That's what I want to find out when it's going to reach that point. N sub O is the 650. E is E to the negative 0.0247 t. So we're looking for t. So again, we're looking for a variable that's in an exponent. So we can take the log of both sides. Since we're dealing with the natural log, or e as our base, we'll use the natural log of both sides. Oh, actually right here, I'm going to divide both sides by 650 first. I need my calculator. So on my calculator, I need 200 divided by 650. 0.3076. So I'll go to 0.308. Or should I just leave it as a fraction, maybe? I probably should. Okay, I'm going to leave it as a fraction for now so that I have a more accurate solution. Okay, so I can write that as 20 over 65 though. So that's equal to e to the negative 0.0247t. Now I would take the natural log of both sides. And now, so I'll have the natural log of 20 over 65 is equal to the natural log of e. That will just give me the negative 0.0247t. And then I need to divide both sides by 0.0247. 0.0247, and that will give me t. Now I'm going to use my calculator because now I have everything I need to know calculated. So when I open this up, clear this off, first I need to take 20 over 65, and then I'm going to take the natural log of that number, and then I'm going to divide that by the 0.0247, and I get negative, I can't get negative. Did I have two negatives here? I should have got a negative when I took the natural log of 20 over 65. It's a negative, okay, and then I'm dividing by, I see my mistake, 0.0247 negative, so I get a positive 47.7 days. All right, so that would be your answer then for this problem, and so 47.7 days, and that's accurate enough for us. And that, like I said, is the last problem on your worksheet. So our answer for this problem would be the 47.7 days. All right, thank you very much, and have a great rest of your day. Let me know if you have any questions.